In today's presentation, we are going to find out how to calculate graphically and numerically the pH and the concentration of all the species. We are going to see 4 examples. We start from a weak acid or base. The methodology is always the same. Write all the reactions, define which are the constants, identify the species involved, and write the charge and mass balances. These 4 examples start from a weak diprotic acid, acid salt, which has a hydrogen in the anion, a salt that doesn't contain any hydrogens, and a salt whose equilibrium is focused on the cation. In the first case, it could be a carbonic acid solution with a concentration of 0.2 molar. We are going to start with the first example, a weak diprotic acid. We're going to calculate the concentration in equilibrium of all species of a 0.02 molar carbonic acid solution. All the constants will be in the tables.
Let's start the example. The first step is writing the different equilibrium reactions. Here we can see the different equilibriums. The equilibrium of the first dissociation is where the acid hydrogen cation is released. The second dissociation is equilibrium where the second hydrogen cation is released. And finally, we have the water equilibrium. To each equilibrium reaction it corresponds an equilibrium constant, which is the second step. This constant is defined as a multiplication of the concentration of the products divided to the concentration of the reactants. In the case of the water equilibrium, this constant does not include the concentration of molecular water as it is the solvent. Ka1 can be known from the pKa1 given by the exercise or found in tables. It is 10 to the minus value of the pKa. The Ka1 is always to the constant of the first dissociation, while the Ka12 is the second dissociation. The fact that the value of the first dissociation constant is much greater than the second constant indicates that the first dissociation is generally predominant, but it depends on the part of the logarithmic diagram where we are. Now we should identify the species involved. There are always the species of the aqueous solution, as well as the ones of the specific compound depending on the exercise. In this case, we have hydrogen cation as positively charged species, while hydroxide, carbonate, and hydrogen carbonate anions are the negatively charged species. Finally, we have carbonic acid and water as molecular species. All species are included in the mass and charge balances except water, as it is the solvent. The mass balance is defined as follows. The initial concentration we are given is equal to the sum of all species of the compound in equilibrium. In this case, they are the different ions obtained when carbonic acid loses 1 or 2 hydrogen cations. The initial concentration of the weak acid is distributed in the different species in equilibrium in a way that the total concentration is the same as the initial concentration. No mass can be created nor destroyed. The charge balance is different. Here, the concentration of positively charged species is equal to the sum of negatively charged species. This is due to the fact that the aqueous solution is electrically neutral. As the carbonate anion has 2 negative charges, its concentration is multiplied by 2 to compensate and maintain the neutral equilibrium. To simplify calculations, we check in the logarithmic diagram which species can be neglected, simplified from the mass and charge balances. We can neglect those species that if we eliminate from the balances, the error is 5% or less. The error is 1.3 logarithmic units in the diagram. You can try to demonstrate this relation between the 5% error and the 1.3 logarithmic units. Here we see the diagram. The three species of carbonic acid are drawn with different color, and the sum of the concentrations is on an imaginary horizontal line at the initial concentration of the substance. The first question we need to ask ourselves is in which part of the diagram we are located. As the exercise started with carbonic acid, we are in the area circled where its concentration is maximum. Now we have to check which species or which lines are more than 1.3 units under the red line. The carbonate species, the blue line, and the hydroxide anion are far below this line. Therefore, they can be eliminated from the charge balance. Now let's see the mass balance. In the diagram, we can see that the lines of hydrogen cation and hydrogen carbonate anion cross at the vertex of the triangle where we are. The crossing means their concentration is the same as this pH and can be neglected from the mass balance as it is at least 1.3 logarithmic units smaller than the concentration of carbonic acid. But what does being neglected from the equation mean? It is not that there is zero concentration, but that it is much smaller than the concentration to which it will be subtracted in the mass balance, leaving the initial concentration of carbonic acid almost unaffected. With these simplifications, we can now easily find the concentrations of the species present in the system, selecting from the different equilibrium constants the one which contains hydrogen carbonate and carbonic acid to obtain all the information possible and be able to easily find the concentrations. The aim of simplifying as much as possible the equilibriums is to avoid making mistakes when calculating the concentrations with a second-order equation if we have all the terms, all the species in equilibrium. The use of logarithmic diagrams to identify the predominant species in equilibrium is an easy method to solve this type of exercises successfully.
Now we have to look at the equations and decide which one we'll use. Since we know the concentration of hydrogen carbonate is equal to H+, and we also know the initial concentration of carbonic acid, we have to find a constant that considers or includes these three concentrations. In this case, it's Ka1. Ka1, which is a known value, equals x to the power of 2 divided by 0.02. From here, we can find x, which is the concentration of H+ and hydrogen carbonate. Once we know this concentration, with the second equilibria, we can calculate the remaining concentration of carbonate. We substitute the data known, we get the carbonate concentration is 10 to the power of minus 10.3. To finish and answer this problem correctly, we need to write down the concentration of all the species in this problem. Therefore, in this slide you can see how the final answer has to be. Remember to always write the units. In this case, it will be molar. This is very important. We are given the concentration of an acidic salt. We are going to work with NaHCO3, What facilitates comprehension as the logarithmic diagram and the exercise itself will be very similar to the previous first type of exercise. All salts, just because they're salts, are strong electrolytes. This means they have complete dissociation. There is no equilibrium. There is only one way arrow. Salts can be both precipitated, which are found in the solid state, or in solution. But if they are in solution, they are in completely dissociation. The exercise tells us that the concentration of hydrogen carbonate is 0.03 molar. As it is completely dissociated, this means that the concentration of both sodium cation and hydrogen carbonate anion in equilibrium is 0.03 molar. What other data do we have? pK 1, 2, and water pK. We have the same equilibriums with the same constants because the salt comes from the same acid, which is carbonic acid. In the species involved, we have the same species plus a new one, which is sodium cation. When doing the balances, this new sodium cation should be taken into consideration. Let's do the mass balances. We have two in this case. The sodium one, which its concentration in equilibrium is the same initially and in equilibrium because the alkaline nature of the cation. The other mass balance is the one of the carbonic acid. We already know this one. We can only have one charge balance, which is going to be similar to the one from the last exercise, but we have to add a sodium cation in the positive charge side. Now, let's see the logarithmic diagram and check what species can be dismissed due to their very low concentration in equilibrium compared to the other ones. There we have three lines corresponding to the different species. The red line is the acid species, the carbonic acid. The blue line is the basic substance, which is the carbonate anion, which is also the predominant in the right part of the diagram at a high pH. Finally, in the middle, we have the black line of hydrogen carbonate, which is the amphoteric substance. What means that it can be either an acid or a base, both giving or gaining hydrogen cations. Now the question that we have to ask ourselves is, in what part of the diagram do we find ourselves? As the initial substance was sodium hydrogen carbonate salt, the initial concentration is the same one as the hydrogen carbonate anion, which means that we are in the central part. In this part of the diagram, the concentration of both the protons and the hydroxide anions are much smaller than the initial concentration of hydrogen carbonate, which is much more than 1.3 logarithmic units, so they can be dismissed from the charge balance. In the mass balances, however, any species can be dismissed as their concentrations are much more similar in this area. What should we do then? We write down what equations we have at this point, and we see that the concentration of the sodium ion in this equilibrium is in both charge and mass balances, so they can be equalized to obtain this, and then substitute the equation with the sodium cation isolated into the charge balance. Once this equation is written, some terms can be eliminated from each side, the hydrogen carbonate one, and the one of the two carbonate ions on the left side, with the other one on the right side. Therefore, the concentration of carbonic acid in equilibrium is the same as that of carbonate anion, 0.03 molar. If we are asked to find the pH of this solution, we only have one substance. It is found by looking at the x-axis of the point corresponding to the inferior vertex of the triangle of the area we are located in the diagram, where the predominant species is our initial substance. In this case, it would be around 8.3. To know the concentration of all the species involved, we have to look at our equilibria, the same ones as before, and we will obtain a new equation that is an addition of the first and the second dissociation. When we add both, we get the equation that we can see at the bottom of the slide. Carbonic acid dissociates into H plus 1 carbonate. The associated constant of this equilibria equals Ka1 multiplied by Ka2. When we add equations, we multiply the constants. When we know the H plus concentration, we can go to the mass balances of hydrogen carbonate, and we can see that we hadn't disregarded the other species, but we can disregard them now because they are in more than 1.3 logarithmic units. The hydrogen carbonate concentration in equilibria is 0.03. Knowing this concentration, we can find out the carbonic acid concentration. Knowing the carbonic acid concentration, using the Ka2 constant, we can calculate the carbonate concentration. As a summary, we will write all the concentrations of the different species in the same slide, or in your case, piece of paper. Now let's have a look at the third example. We have a potassium carbonate solution with a concentration of 0.03 molar. It's a salt, so it's a strong electrolyte. It's completely dissociated, and we know the exact concentration of potassium cation, which will be 2 times the initial concentration, since it has a coefficient rate of 2. We know the initial anion concentration is 0.04 molar. We have to follow the same steps when taking into consideration the constants from the table. We have 2 mass balances, the potassium cation and the carbonate one. We can also see the charge balance. What can we disregard? The first thing is to know in what part of the diagram we find ourselves. We started from carbonate, so we are on the right side, which is marked with green. In this point, the carbonate concentration is greater than H+, so we can disregard it. While in the mass balances, we can see that the carbonate concentration is greater than the carbonic acid. We get an equation that gives us more information than before, when hydrogen carbonate would have equaled hydrogen carbonate. The carbonic acid can be disregarded because it's bigger than 1.3 logarithmic units. Let's see how to proceed numerically. The potassium concentration divided by 2 equals the carbonate concentration. If we equal these 2 equations and we substitute them in the charge balances, we can simplify the hydrogen carbonate and the carbonate anion. The OH concentration equals the hydrogen carbonate concentration. My recommendation is to do it by yourselves at home because it's simple, but it's important to know the steps. In the logarithmic diagram, marked with the blue arrow, we can see the point where these 2 species cut. Substituting in all the equations, we can calculate the concentration of all of them. In this case, the one we can disregard is H+. So we will substitute K omega divided by the OH concentration. In this point, when we get to the hydrogen carbonate plus the carbonate concentration equals 0.04, we can question ourselves if we can disregard hydrogen carbonate. We are in the limit. It's 1.3 logarithmic units. Let's calculate what happens if we disregard it. If we disregard, we substitute and we get that the concentration of carbonate is 0.04. And from there we find the concentration of all the other species. We get a pH of 11.45. But what would have happened if we hadn't disregarded the hydrogen carbonate? If we don't disregard any of the species, we have to solve a second-degree equation. Instead of having hydrogen carbonate to the power of 2 in the denominator, we write 0.04 minus the carbonate concentration. Substituting and solving the equation, we get a pH of 11.44. The pH difference is very, very little. Last but not least, as we have seen in all the other examples that we have done so far, we have to substitute all the equations and calculate all the concentrations, and then write each species with its concentration and the unit. Let's start with the fourth example. In this case, we have a salt with an equilibrium in the cation. We have an ammonium chloride solution with an initial concentration of 0.03 molar. In this case, we have to write the equilibrium. We start from a salt, which is completely dissociated, and we know the initial concentration of both the cation and the anion. Now, the cation is the one that is found in equilibrium, with a pK of 9.25. The anion chloride is not found in equilibrium. Therefore, the chloride concentration will be constant throughout the problem. The initial chloride concentration will be the same one as in equilibrium. Let's have a look at the reactions. We have NH4 plus in equilibrium, and we also have the dissociation of water. We can also define the constants. And finally, we identify the species involved. As positively charged species, we have H+, NH4+. As negatively charged species, we have chloride and OH-. And as molecular species, we have ammonia and water. We do the mass balances. We always have 2 because it's a salt. That means NH4 can be found as a cation NH4+, or NH3. In the charge balance, we equal the positive charges to the negative charges. If we have a look at the logarithmic diagram, since we start from the ammonium cation, we find ourselves in the left. We can disregard the OH- concentration. We don't disregard NH3 nor H+, because we want to mathematically play with these equations to equal them. In the end, we will be able to disregard them. We have the charge and mass balances. If we equal the two mass balances and we substitute the charge balance, we get the equation from the slide. NH4 is found in both sides, so it can be simplified. The H+ concentration equals the NH3 concentration. This is the cut point from the graphic, which is indicated by the blue arrow. Substituting in the equilibria, we can calculate the concentration of all the species. The final pH is 5.39, and then we can find the concentration of all the other species.